nanocomposites, the electrical independence, and present
the last one.
Alexopoulos.
Yes, Nicola. Nicola. Okay, how's that one? Yeah, up and down. Like this, okay.
Yeah, flip it, I think.
Sorry?
Flip it. The pointer, flip it.
Oh.
Yeah.
There it is. Okay. Thank you very much, all of you, for being here. I will present you the work entitled Evaluation of Fracture Toughness in Graphene-based Cementitious Nanocomposites via Electrical Impedance. So, as you can guess from the title, we are evaluating fracture toughness. Electrical impedance is a measurement of electrical resistance. So, we try to marry these two evaluation methods. So, this is a work from my postdoc student, Mrs. Tziviloglou, together in collaboration with Associate Professor Metaxa, George Maistros from Advice, Kourkoulis coming from National Technical University of Athens, and myself. Okay, just for motivation, you are all aware you're coming from the cement industry or from the construction building materials. You know the advantages and disadvantages of cementitious materials. But their main drawback is cracking, as you all know. So we have to find some routes to incorporate or make this disadvantage into an advantage. With regard to repairing, you all are aware that we have seen the plenary lecture by Professor Ferro, saying that we need a lot of billion to maintain or repair cementitious infrastructure. So one possible solution might be some additives targeting either reinforcing at the micro level up to till the last decade or at the nano level during the past decade. I will include my presentation is dedicated on the reinforcement at the nanoscale, and at this period of time we are working with graphene nanoplatelets. For those of you that are not aware of graphene nanoplatelets, it's actually carbon, atoms of carbon structured into layers. So it is considered as a two-dimension material at the nano level. And what do we need the carbon nanoplatelets is because besides the cracking resistance, they also promote at the appropriate levels, they also promote electrical properties. We are transforming the non-conductive matrix into a conductive matrix. And any cracking or any damage could be detected by our matrix, which acts as a resistor. So to this end, we perform some three-point bending test. This is ordinary Portland cement. Yes. And this is the sketch. It's a 20 millimeters width, and we had a starting notch of 5 millimeters. So it's 1 out of 4 is notched. We have used the respective standard to measure the K critical stress density factor, or in the literature is also referred as K1C because of the high width. And in the meantime, on other specimens, we have measured the electrical conductivity. You can see the electrical setup down here. It's on the two-wire method. There are two electrodes, voltage with AC. So voltage comes, and then we measure the impedance of electrical impedance of the bulk of the material. So with regard with the mechanical behavior of the specimens. Actually, we have investigated several different content. On the x-axis, you can see different content of graphene nanoplatelets, and as you can see, for the very small reinforcement at the 0.05 weight percentage, you can have an enhancement of approximately 29–30%. So this is according to the literature, because even at the so small contents, reinforcement takes place, because they are reinforcing at the nanoscale. So nano cracks are prohibited to be promoted. So that's why this enhancement is also evident. With a higher concentration, we see that you can see that there is a lot of scatter in the mechanical in K1C, but this is again the higher increase does not promote a uniform dispersion of the nanoparticles. So this is because, of course, that higher concentration, the graphene nanoplatelets tend to agglomerate, and that's why this kind of reinforcement is no longer valid. But when compared with the reference one without any nano reinforcement, yes, you also have a substantial increase of the order of magnitude of 14–17%. With regard to the electrical impedance, is typical for surface science. We use them to measure the electrochemical impedance is the resistance we use for imaginary and non-imaginary part. You can see that you have some plots like this. It comprises out of two arcs scanning from the lower frequency up to the higher frequency, and for different, as you can see, for the different concentration, you see a cusp point that, according to the literature, is the typical value for electrical resistivity. So this cusp point gives us information about the resistivity of the bulk resistivity of the material. So with this easy to perform method, we measure the electrical properties of the new material. If you can plot the results, of course, with the relative scatter being extremely low, you can see that the resistivity decreases and then increases. This is again highly connected with the dispersion capability of the carbon of the graphene nanoplatelets. But one idea we had from the group is, why don't we have the results from the mechanical behavior, we have the results of electrical resistance, can we actually make a connection between these two by default not connected properties? And the question is, the answer to the question is here. This is what we actually propose at the preliminary level. Of course, you can see the red level is K1C, the resistance is the black one, and if you make this comment, and if you can see the trend is inverse. So we thought simply to make a trend line of K1C at the y-axis and inverse of resistance at the x-axis. And then you can see that you have a perfect, direct, linear correlation. That, of course, is something that we first report, and we need to investigate it into other kind of materials, more different kind of graphene nanoplatelets, and so on. But this is something that triggered our understanding, and we need to report it. So, this is our preliminary results, and I would like to thank you very much for your attention.
Thank you, Nicola. Are there any questions? Please.
You can go first.
So this is basically a method for measuring the KIC, and you want to, but your long-term goal is to turn it into a measuring.
We're measuring K1C, yes,
Yes.
and the other method is the ohmic resistance of the bulk material.
Yeah.
And these are properties connected because if you have lower electrical resistance, this means that electrical current can pass.
Yeah.
Okay, so this means that you have a good reinforcement of the dispersion of the nanoparticles. This means that if a crack tries to transpass, then it has specific obstacles to cross. But this is something that we have to...
So you basically measure the disbursement of the nanoparticles.
Exactly. With electrical resistance, yes, you can measure the dispersion. Exactly.
And then you hope that you could also turn that into a measuring device. Because you see, you could when the resistance go up, then you have crack inside.
Yes, you know, yes, with
It is in fact a structural health monitoring attempt.
Yeah.
Nikos and the team suppose that if we can measure the electrical resistance and observe these changes, it means that something happens, which is obviously crank generation. That is why we want to apply this technique for the cement materials used in structural restoration of monuments.
Increase of resistivity means that the dispersion is not well performed. Dispersion is due to the highly content usually, because if you add some more, then they tend to agglomerate and they are not equally dispersed within the matrix. So as you can understand, this is when a crack tries to break this matrix, then it will easily go at the agglomerates, at the interface of the agglomerates, and not have a real enhancement in crack stopping.
Have you also considered the influence of reinforcement bars?
Yes.
Because they are I forgot how could they connect.
Yes, this is one type of GNPs, one type.
Yeah.
We are investigating at the moment 3 other types of GNPs, other with higher lateral size, higher width, and so on, just to make a more parametric study of this one.
Good, yeah.
Other lady?
Please.
Okay.
Another question? Okay. Take your Nicolas.